the valence shell. And then how do we define an insulator? 5 to 8, and then a semiconductor is always 4. Right? It's neither considered an insulator or a conductor. Then what do we do to change its conduction characteristics? Huh? Yeah, we call it doping. And then, so semiconductors use what we call a covalent bond, right? And what's a covalent bond? Yeah, good. And so one way we try to get a covalent bond is to share electrons in the valence shell until we get 8, right? Okay. So if we had, it would take 4 semiconductor devices to do a covalent bond, because each one of them is sharing 2, right? Does that make sense? So it's got 4, and then we have 4 more that shares 2, which ends up with 8, and they bond real well. And this is what we call a crystal. So a silicon crystal is made totally of covalent bonding, where everything matches up. Then we dope it. We introduce. The book will say impurities, but actually they're not. They're impurities relative to semiconductors, right, or a semiconductor. And we have 2. What's the 2 that we have? Well, not. I don't want the material, but we do what we call a trivalent, right, or we do a pentavalent. And the trivalent creates an absence of electron in the bond. So an electron would carry a negative charge. So if we got one in, now this P material is not charged. We just call it P material because it's looking for electrons, right? You understand? So P material has no charge. But what we end up with is we end up with a bond. Let me bring up the PowerPoint real fast. Love our network. No, I forgot. Well, we had interviews yesterday, and it was basically the whole time I was here. Well, I'm true. And then as soon as I got out of interviews, I had to go to class. I teach a night class. So this is basically a covalent bond here, where they create this. Then out here we would have 3 more, and up there we have 3 more. And we go out and we actually create what we call a silicon or a crystal. Now here we're dealing with silicon, which is by far the most widely used silicon. There are others. We do use a little tin and lead and stuff like that to make special devices. But the main semiconductor that we use, the 2 main ones are silicon and germanium. By far, silicon being the most. So this would be a silicon crystal using covalent bond to create molecules. Right? And then we came over here and we talked about when we heat silicon, when we heat just about any material up, when we heat almost any material, then what that does is it becomes more active, and then we come up here and we can actually pump electron out, which creates what we refer to as the hole. Semiconductors, we call it a hole. Basically, that's just a place looking for a what? Electron. Make sense? And then, of course, it'll come back, it'll fall down. So semiconductor, and if I pump an electron up out of here, it's basically what we call a free electron. We can easily make it move. So this is one problem we have with semiconductors, is they vary their opposition with heat. The more we heat them up, the more conductive they come. The more we cool them down, the less conductive they have. So semiconductors can go into what we call thermal runaway if we don't do something about that. And that's why a lot of semiconductors have heat sinks on them. They have fans blowing on them just to try to keep them from going into thermal runaway. The next thing we do, of course, we looked at this, and by the way, what's really neat is that out here in the wire, in the conductor, and in the power source, we have two things flowing in two directions. And the analogy I use, of course, is a glass of water. And, so I come up here and I have 8 glasses of water and one of them's full. And then I start pouring them one to one. Well, that would be like electrons. But so the electrons are moving from negative to positive, but the empty glasses are moving from what? Positive, negative. So every time you push an electron out, you create a hole. And those holes are moving from positive to negative, and the electrons are moving from negative to positive. So there's actually two things moving in the conductor. Y'all follow that? And so we teach two currents. Most engineers use what we call, they call conventional current. Conventional current is teaching hole flow. Current flowing from positive to negative. But what we actually know, the actual thing that's actually moving is an electron. So most two-year colleges and most military, the military teaches electron flow because that's actually what's moving, right? Y'all understand that? Unfortunately, when they started devising the symbols for semiconductors, they're designed around conventional current flow. Inside this material right here, we don't have hole flow. We got nothing. These pump up, and that's not exactly. The majority of carriers is going to be what? Electrons. I'm sorry. And here we have both of them, but when we dope them, we end up with majority carriers. So let's look and see what we're doing. So this is basically the way it flows through a conductor. We okay? And then we got this guy. And this is, oops, wrong one, Rich. So what we do, of course, is we fuse them together and form a what? A p-n junction. And as soon as we fuse them, so what we do is we introduce, and this is, I got a really good video. So what we do is we dope these things with either pentavalent, and I gave y'all some pentavalent material, right? I thought I did. No, this is the wrong one. That's what it is. It's still the wrong one. It still looks like the wrong one. Huh. Yeah, I don't have a PPX. So we dope it, we come in and we take the pure semiconductor and we introduce either a trivalent. So what happens when we do a trivalent, if we were looking at the bond, then we end up by creating a hole, right? Everybody okay? So I've got my electron. Up here I'd have a minus minus. Over here I'd have a minus minus. Over here I'd have a minus minus. Over here I had a minus. And what am I missing? I'm missing a minus, right? Because we doped it with a pentavalent. So they bond together and we automatically create a hole. This guy right here we call, once we dope it, we call this P material. Not because it's positive charge, it's that it's attracting electrons. We call it a P material. And it doesn't stand for positive, it's just what they named it, right? The other one, we come in here and we bond it with a pentavalent. So we might have one here, 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 and over here we might have 3, right? You understand? So that guy's not bonded to anybody because it can't be in the valence shell, because the valence shell can have what? A. So what's this guy doing? He's just floating around in there. He's jumping all over. It's just all over there. So N material does not have a negative charge, but we called it a negative charge because this free electron is looking for a hole, right? Y'all understand? So we call this N material. And then what we do is we come up here and we bond these together. And we call this a p-n junction. And this is where things get very interesting. Okay? So this is what happens. As soon as these things fuse together, holes on the N material, the electrons in the N material fall into the holes. Over here, we come over here and fall. Let's go back. This is, somehow we're missing a slide, guys. So what happens if I come over here on a P material just by itself? P material. And what we have in here is we've got these guys looking for a hole, right? You understand? It's not, that makes sense? And if I come over here and put this thing across the battery, I'm going to have to put a resistor in there because it would act like a short. Then what happens is the holes that's flowing this way will come into this side, and then the holes will flow through here, and then they're going to combine with the electrons over here, right? Does that make sense? So in a P material, the predominant current flow in a P material is not electrons, it's holes. Because those have the guys, those are the ones that's free to move, right? So it's not like in the conductor. In the conductor itself, we have what? We have electrons and holes. Right? You understand that? Inside the pre-material, we predominantly have holes. Now, there are some electrons in there. For one thing, we cannot make perfectly pure or intrinsic semiconductors. And another thing, when you come up here and heat this thing up, then what happens? Then automatically some electrons pop up into the conduction bank. We call this leakage current. So the majority carriers in a P material is what? Is holes. And then we do the same thing with N. So an N material's got all these electrons just moving around. I come up here and put a battery across here, or a DC voltage source. I got to put a resistor there. And then this guy over here is going to push the electrons that way. When it hits that side right there, it's going to recombine with the holes coming from the conductor, right? You understand? So the predominant carrier inside N material, we call it the majority carrier, is what? Electrons. And the minority carrier is holes. And it's just opposite here. So minority and majority, right? Okay on those. Now, of course, when we combine these things together, we've got the N material. These are minority. We've got the N material trying to give away electrons. We have the P material trying to find electrons, right? To complete that A in the outer shell. So what happens is the instant they are bonded, then we got electrons that fall into here. We got holes that fall into here. And then what we end up with a region here that has no majority carrier. We call it what? We call it the depletion rate. Now what it creates is now it creates ions, because now the protons and the electrons no longer match inside the material, which means we create a small little battery inside there that the resistance of the semiconductor is so high that we can't get current out of it, but we still have to exceed it before we can cause current to flow through it, right? Does that make sense? And we call that the barrier voltage. Or the holes come in there.
But I'm saying the leak is the same on both sides.
Well, all we don't know, all we know is that with temperature, the leakage current goes up and it cools down. Now, where the majority carriers are going through, so it'd have to be the same. You're right, because for every electron we have, we'll create a hole too, and then they fall in there. And we'll look at what we call the leakage current. It's very, very low. It only comes into play when we come up here and put a potential across a p-n junction. So on Blackboard, these devices that have a single p-n junction, we call these diodes. And so we can go to Blackboard real quick and look at a data sheet. So we got one called data sheets. And a data sheet or specification sheet tells you, first of all, it tells you the maximum conditions you can run this thing in. And then it tells you where you're supposed to operate in. So we're going to look at a small signal diode, and we'll talk about the different categories. So don't like me, does it? Third time's a charm. Huh? There we go. I think we got all the students next door on. So over here in our main menu, since we're going to be doing this a lot, we're going to be dealing with the semiconductor devices. We got a link to data sheets. And we'll look at this. This is what we call a rectifier diode. This is a really standard one. It carries part numbers between 1 n. So most diodes start with 1 n because there's only one junction. Most of your transistors start with 2 n because there's what? Two junctions. These are all JEDEC registers. Joint electronic devices registers these numbers and also characteristics. So one of the things we're looking for is the barrier voltage. Let's see. I'm looking at the 40X. But it's in there too. We're looking for a specification called VF. Here it is right here. For this diode. And it's typically what? About 930 millivolts. Maximum would be what? 1.1. But what you find out is that it changes with temperature. So what they do is they come up here and give you the temperature where it was set up in. And 25 degrees centigrade is very standard for solid state devices. Here's your leakage current right here. So the maximum it ever be would be what? 10 microamps. That's the worst case, as long as you didn't break it over.
typically it's around 50 nanoamps at 25 degrees. At 100 degrees centigrade, it's at about 1 microamp. And that's that's not much, right? So you can see it varies in temperature. They give us 2 ratings, right? There's a lot more to go. So we're going to have to be careful what temperature range we operate this thing in, right? And here it tells us the actual operating temperature range that this guy's to work at. So as long as I operate it between -65 and 175, which is real hot, degrees centigrade, then it should be okay, right? If I get above that, then it might be damaged.
I'm looking at the small system, and it's saying that the only thing I see by temperature is 25 degrees Celsius.
I say centigrade. By the way, centigrade is an old term. It's actually been moved over to centigrade. I mean Celsius, by the way. I think we're bringing that up.
But it says it doesn't seem like a brain. I see.
Yeah, but every temperature, every data sheet is going to be a little different, right? You understand, because especially if they're made by different manufacturers. And this is an open technology diode. So how many different companies make 1N4001s? Anybody that wants to, because it's open technology. All they got to do is make sure that it meets the specifications. If it meets these specifications, then they can put a 4001 on there, right? Or 4002 or 4003. This diode is what we call a rectifier diode. It's not used in high-speed switching applications. It's used strictly to, and what do we say a rectifier does for? Converts AC to DC. We just touched on that the other day. So what happens when we come up here and form that p-n junction is now we create a unique situation where we can come up here and bias it. Now, what does bias mean in semiconductors? Well, it's a DC voltage. Semiconductors are DC devices. Even though we use them to convert AC to DC, it looks at the alternation on AC like it was a DC quantity. So bias is a DC voltage that we apply to a semiconductor that sets its operating characteristics. So we have two. We have reverse bias and we have forward bias. So the first one they show us is forward bias. So what we do to forward bias is pretty straightforward. If we put our negative polarity pointed toward the end, we take our positive polarity and point it toward the tip. Now what happens is I've got all these free electrons floating around there. Let's do another color. So I've got all these free electrons floating around in here. Right? And then over here, I've got all these holes looking for electrons. But the problem is I've got this little barrier potential setting right here. Right? And for silicon, it's approximately 7/10. Now we don't know because it varies, right? Or 700 millivolts. So what happens when I come over here and put this negative right here, what's it going to do to the electrons? What does like charges do? Repel. So it's going to force these guys here toward there. What does positive charges do? It's going to force these suckers right there. And so what's going to happen is these electrons are going to start falling in holes. We're feeding holes from the conductor into this side. It's falling into electrons, and we have current flow. And here it's going to be holes. Over here it's going to be electrons. And they just do what? They just merge right there in the center. You got electrons looking for holes. We're forcing holes toward the junction. We're forcing electrons toward the junction. They just do what? They just combine and fall right into it. But to cause this thing to happen, we have to collapse that barrier potential. We have to push it through the voltage source, right? You understand? So that means if I was to come over here and this was a 10-volt supply, what I would do if I measured that right there, I would see it measures around 9.3 volts. And then if I measured across this guy, we would see it's approximately 0.7 of a volt. Now I'm saying approximately because it varies, but what we find out in semiconductors is we use a lot of what we call approximations. It's just like DC. When you were taking DC or even intro and you're introduced to Ohm's law, right? You understand? Your math is perfect, but your components are not. So in intro, what you did is you carried your measurements out or your calculations out to like 3 decimal points because you were trying to prove a law. After that, guys, we don't worry about that. We just know if I calculate 7.3 volts and I measure, 7.9 volts, that everything's fine. It's just what was the difference between my calculation and my measurements is the tolerances of the devices themselves. So when you do math in electronics, you are not calculating precise. You're calculating what we call approximations, right? You understand? Approximations. And we'll talk about the 3 approximations we use. We use what we call second approximation, which means here we'll use 0.7. First approximations is we assume the diode doesn't drop any voltage at all. We consider it to be what they call an ideal diode. And it's okay, because I calculated, I say, okay, this resistor should drop 7 volts, 10 volts, and it's dropping 9.3. Well, it's close enough that what could be called, it might not even drop 9.3. It might drop 8.4 because of the tolerance of the resistor, right? You understand? So first approximation, you assume the device to be ideal. Second approximation, you use 0.7 for silicon, and we use 0.3 for germanium. Third approximation, which means you actually look at what we call a diode characteristic curve, which means it starts up here. As soon as I put voltage, we have just a little bit of current flow through the thing, right? And then when we get around 0.5, we start seeing a knee. And then when we come up here, and then it goes up on a slant like that. Now, why does it slant? Because the device, there's no way in the world we can't have an R inside that. So now what happens is the actual output is linear depending on the amount of current flow we try to put through it. So this is the actual, what we call a diode characteristic curve, or this is F. This is VF, forward bias. So VF stands for forward bias, right? And then this right here would be IF. This would be the forward current right there. So if the current goes up, the diode's going to drop a little more voltage. If the current goes down, it's going to drop a little less because it's not a closed switch. It's a device that has the resistance in it, right? You understand? So there's no way in the world I can keep this thing from having zero resistance. Ideal, what we call a second approximation, we would come over here and at 0.7 of a volt, we'd go straight up. So no matter how much current we're putting through it, we'll always assume 0.7 of a volt. This is what we'll use most often in this class. No, ideal means we come up here and I'd have to draw it. I would have to draw it in a different color. Ideal, we'll assume as soon as we forward bias it, that sucker goes up. This would be what we call first approximation. This is what would be called a second approximation. And this would be what we call third. So third might be what an engineer looks at if they're under really, really tight specifications on exactly how much voltage the guy would drop when we had 5 amps of current flow through it, if it could handle 5 amps. What we're going to do in this class is to make sure you get, now if you're dealing with, 500 volts, then we'd use first approximation, because what's 7/10 of a volt to 500 volts, right? You understand? So the higher the voltage, and usually the crossover is around 50 volts, where anything above 50 volts we'll probably use ideal. Anything below that we will probably use second, right? And then only engineers use third. Now, this is what we call forward bias. So rule of thumb is that when we forward bias it, it acts like a closed switch. It's not a closed switch. A closed switch, if it's a good switch, will drop how many volts? 0. This guy's going to drop volts. And the voltage goes up with current. But it acts like, but this is not me going over and flipping a switch. This is just by me putting forward bias on the thing, right? You understand? Now, when we come up here and reverse bias it, so this is what's happening. Now, this is a really good picture. This is not a good. So in here we have hole flow, and here we have electron flow, right? You understand? And they just do what at the junction? They just merge. Where are the holes coming from here? Well, the holes are flowing in the conductor anyway, so it just feeds in. These keep feeding into the feed to try to get the right right bonding. These just feed into here, trying to get the right bonding, right? Which is pretty neat. So inside a semiconductor, basically we have current flowing in one direction. Huh? This is the barrier potential. This is reverse bias. This is what's neat. So how would we reverse bias? They don't have a resistor here. What we do is we point the watt in toward the P. We point the watt. Yeah, the plus, we point the plus toward the E. And what's going to happen is, as soon as we do that, these electrons, some of these electrons are going to spill out, and what happens to the barrier? It gets bigger, and the current flow stops. Almost. The only thing we have now is what we refer to as what? Yeah, and what controls the amount of leakage current? Well, voltage and temperature, primarily by temperature once you establish a voltage, right? So that means if we reverse bias it, it acts like a what? Open switch. If we reverse bias it, acts like a closed switch. And this is automatic, guys. We don't have to go up there and flip the switch. All we got to do is change the polarity on the diode itself, right? However, well, some voltage is going to bop over. But you got to remember, so what we have, if we look at the data sheet, if I still got it over, and this is what, there it is. What we're doing is looking at these absolute maximum ratings. And it calls peak repetitive reverse voltage. This is the breakover voltage right here. For the 1N4001, everything else is the same between these different part numbers. The only thing that varies is where these things break over at. So you got this sucker, you caught this sucker, and this is what the characteristic curve looks like using third approximation.
And you can take the same diode and set it up, reverse forward.
No, what we do is we use this characteristic, and I'll show you. So these guys can do logic. They can do it. Normally we don't use a rectifier like diode to do logic, but we can do ands and ors. And then later on, we'll combine it with a transistor, and we can do nands and nors. They can't do knots, but we can do a knot with a transistor. If y'all know what those mean. Oh, I can't drive on this. But if I come over here and this guy here is dropping 50 volts, and then I force a lot of current through it, then you're going to create a lot of watts real fast, right? You understand, and it's going to bother it. But so this is what we call the breakover voltage. Most textbooks call this PIV, which is peak inverse voltage, but data sheets calls it DRRM. I've never seen a data sheet call it PIV. And this is where books teach PIV, and then data sheets call it DRRM. So this is what varies between a 4001 and a 4007. A 4007 has a breakover voltage of what? 1,000 volts. A 4001 has a breakover voltage of 50 volts. We'll be using 40. So I could replace a 4001 with a 4007, but I could not replace a 4007 with a 4001. Makes sense? Because if the engineer put a 4007 in there, it's because of the breakover voltage. But all the other down here in the characteristics, it don't specify which version this is. It's just the breakover voltage that varies between those part numbers. So breaking over voltage, what would happen is, let me go back to my data sheet, where I can draw my PowerPoint. So the characteristic curve would look like this. Over here, around 0.5 of a volt, it starts conducting, and then it goes up at a slight angle. Over here, we come over here, and this is leakage current, and then we get to a point where we've got so much voltage across it, it breaks over. I'm going to put a line right there because it's going to be on there. This is bad for a standard diode. If you break that sucker over in reverse, it's usually gone just like that. And the problem with resistors, when we exceed the rating of a resistor, usually when it starts going, I've never seen a resistor short. Usually when you overheat it, the resistance goes up and then you screwed it up. Diodes, when you break them suckers over, they can either short, they can become leaky, or they could open. So solid state devices could actually short. And then you got big problems, right, if you break them over. So this is why we make sure when we go to the lab in this class, you're going to wear your safety glasses. A lot of these things will pop on you. You don't create enough to knock your eye out, but it could definitely cause problems. You get that plastic in there. So reverse bias, a diode causes current to become practically zero. However, there is a small amount of current that is produced by minority carriers in, we call this what? Leakage current, and this is IR in the data sheet. But remember, typically it was like in the nanoamps, right? And it's there. It's just that normally it's so small we can just do what? Ignore it. Now, the symbol for these things is going to be our arrowhead, and it's supposed to be filled in, but a lot of people leave it out because it takes a little time. And then we have a bar, and then we bring in or put the other lead. This represents the P material. This bar represents the N material. Now, before this, we were dealing with vacuum tubes. A vacuum tube diode would look like this. We would have a thing called a cathode, and then we have a thing called an anode. What would happen is they have a little heater right here. And what happens when you heat it, then this substance right here releases a lot of electrons. If I come up here and make this positive, then we would have electron flow. If I made it negative, if we swapped it around, then it would block it. So the first diodes were vacuum tubes. But the name of this guy, they gave it the what? Anode. The name of this guy, they gave it the cathode. So guess what? This N material, what do we call it? We call it the cathode. And the P material, we call it the anode. Now, what they do to show you this is they, on the diode, is they put a stripe that indicates the cathode. In fact, I'll go over and get one of these. So this is a 40, these are the 40,000 series. And then this is a 1N914. This is a small switching diode. So when we look at this, guys, what's the first thing you know? So here's, of course, here's the leads. You see that around it. That identifies the cathode. So if that's the cathode, the other side has to be the what? Anode. And then if I look at the 914, you notice it's got the same, uses the same technique. Here they use a black wire, a black circle, that's the cathode, and the other lead is the anode. Yeah, my computer just went black, the screen went black.